Imagine a world where days are drastically longer and the very shape of our continents has shifted. This isn't science fiction. It's the inevitable outcome of a powerful, relentless force that has been subtly reshaping our planet since its birth. Join us as we uncover the astonishing truth about the moon's ongoing tidal tug and what its invisible grip means for the future of Earth and all life on it. Chapter 1: The Cosmic Ballet, Earth and Moon. What truly pulls the ocean. Watch a time-lapse of the tides and you'll see the rhythmic ebb and flow, a seemingly gentle breath of the planet. But behind this serene spectacle lies a force of immense power, subtle yet relentless. The moon, our celestial companion, often taken for granted, is not merely a distant light in the night sky. It is Earth's gravitational dance partner, locked in an embrace that has shaped our world since its very inception, from the moment of its violent birth, likely from a colossal impact with a Mars-sized protoplanet. The moon has been inextricably linked to Earth. This isn't just a casual orbit. It's a cosmic ballet, a gravitational pas de deux where each body influences the other with profound consequences. The Earth-Moon system is a binary dance, a testament to the fundamental laws of physics playing out on a grand scale. Their gravitational embrace is so strong that it extends far beyond the visible tides, subtly influencing everything from the planet's rotation to its very geological processes. This intimate relationship, often overlooked in our daily lives, holds the key to understanding not just the past of our planet, but its inevitable future. We tend to think of the moon's influence primarily in terms of the ocean tides, a visible manifestation of its pull, but this is merely the most obvious symptom of a far deeper and more pervasive interaction. The moon's gravitational grip extends to every particle of our planet, deforming not just the liquid oceans but the solid land masses themselves. This constant, subtle reshaping has unexpected consequences, hinting at a future where our days are dramatically longer and the very rhythm of life on Earth is fundamentally altered. The cosmic ballet continues, and its steps are leading us towards a future we can only begin to imagine. Chapter 2: Unveiling the Tidal Force. To truly grasp the moon's profound influence, we must delve into the mechanics of tidal forces. At its core, it's about gravity, but with a crucial nuance: the inverse square law. This law states that gravitational force weakens with the square of the distance between two objects. While the moon pulls on the entire Earth, its pull isn't uniform. The side of Earth closest to the moon experiences a stronger gravitational tug than the side farthest away. This differential pull is the genesis of tidal forces. Imagine the Earth as a slightly elastic sphere. The moon's gravity stretches this sphere, creating bulges on both the side facing the moon and the side opposite it. On the near side, the water and land is pulled directly towards the moon. On the far side, the Earth itself is pulled away from the water, leaving the water to bulge outwards. These bulges are our high tides. The areas perpendicular to these bulges experience a relative squishing effect, resulting in low tides. It's a constant dance of deformation, a subtle stretching and compressing of our planet. While the most visible manifestation of these forces is the ocean tides, the solid Earth is not immune. We experience what are known as earth tides or body tides. The solid ground beneath our feet rises and falls by several centimeters twice a day, a movement so gradual and widespread that we rarely perceive it. This subtle deformation of the Earth's crust can even influence geological phenomena. For instance, the minute stresses and strains induced by Earth tides can, in some cases, trigger seismic activity or influence volcanic eruptions, particularly in areas already under tectonic stress. It's a testament to the pervasive nature of the moon's gravitational reach, extending its influence far beyond the rhythmic lapping of waves on a shore. Chapter 3: Beyond the oceans. Tidal impacts. The moon's influence extends far beyond the rhythmic rise and fall of ocean waters, subtly shaping the very geology of our planet. Overeons, the constant stress and strain from tidal forces have played a role in geological processes, including the movement of tectonic plates. While not the primary driver of plate tectonics, the minute, cyclical deformations caused by Earth, tides can contribute to the stresses within the Earth's crust, potentially influencing the timing and intensity of seismic activity and even the slow, inexorable drift of continents over geological timescales. It's a testament to the cumulative power of seemingly insignificant forces acting over vast periods. Looking beyond Earth, the phenomenon of tidal locking offers a glimpse into our own distant future. Many moons in our solar system, including our own, are tidally locked with their parent planets. This means their rotation period matches their orbital period, always presenting the same face to the body they orbit. Our moon is tidally locked with Earth, which is why we only ever see one side of it. This is the ultimate outcome of tidal forces acting over immense stretches of time, gradually slowing a body's rotation until it reaches this stable configuration. This process is not unique to moons. Planets can also become tidally locked to their stars, leading to extreme temperature differences between their permanent day and night sides. Crucially, the moon is also slowing Earth's rotation through a process called tidal braking. As the Earth rotates, the tidal bulges in the oceans and solid Earth are dragged slightly ahead of the moon's direct line of pull. This creates a gravitational torque that acts as a brake on Earth's rotation, gradually slowing it down. In return, the moon gains orbital energy, causing it to slowly recede from Earth at a rate of about 3.8 centimeters per year. This is a profound exchange of energy, a cosmic dance where Earth's rotational energy is transferred to the moon's orbital energy. The consequence for us is that our days are getting longer, albeit imperceptibly in human terms. Billions of years ago, a day on Earth was only a few hours long. This tidal braking is a continuous, relentless force making our days longer over geological time, a silent testament to the moon's enduring grip. Chapter 4: The Slow Dance of Evolution. Lengthening of Earth's day, a direct consequence of the moon's tidal braking, has had profound implications for the evolution of life. Imagine early Earth with days lasting only a few hours. The rapid succession of light and dark cycles would have presented a vastly different environment for nascent life forms. Organisms would have had to adapt to much shorter periods of photosynthesis or foraging, followed by equally brief periods of rest or darkness. This constant, rapid fluctuation could have driven the development of highly efficient metabolic processes and rapid reproductive cycles. The very rhythm of life, from cellular processes to ecosystem dynamics, would have been dictated by this accelerated diurnal cycle. As the days gradually lengthened over billions of years, life on Earth adapted to these changing rhythms. The extended periods of daylight allowed for more prolonged photosynthetic activity, potentially leading to the evolution of larger, more complex plant forms. Longer nights could have favored the development of nocturnal predators and prey, leading to a coevolutionary arms race. The increasing duration of the day-night cycle would have influenced circadian rhythms, the internal biological clocks that regulate many physiological processes in living organisms. This slow, inexorable change in day length acted as a powerful selective pressure, shaping the very fabric of life on Earth. Beyond the direct impact of day length, the changing tidal patterns themselves would have played a crucial role in shaping coastal ecosystems. Early life often originated in shallow, intertidal zones, where the ebb and flow of tides created a dynamic and challenging environment. As the moon receded and the tidal range changed, these critical habitats would have been constantly reshaped. Organisms living in these areas would have had to adapt to varying exposure to air and water, leading to the evolution of specialized adaptations for survival in fluctuating conditions. This could have driven the diversification of species, as different niches emerged in response to the changing tidal landscape. The migration patterns of marine species, the distribution of coastal vegetation, and the very structure of intertidal food webs would all have been influenced by the moon's gravitational dance. Looking into the distant future, the continued lengthening of our days will undoubtedly alter climates and life as we know it. With days potentially stretching for weeks or even months, the thermal regulation of the planet would be drastically different. Extended periods of sunlight would lead to extreme heating, while prolonged nights would result in severe cooling. This could create vast deserts and ice caps, dramatically altering global weather patterns and ocean currents. Life forms would need to evolve extraordinary adaptations to survive such extreme temperature fluctuations. The delicate balance of ecosystems, honed over billions of years of relatively stable diurnal cycles, would be profoundly disrupted, leading to new evolutionary pathways and potentially the extinction of many species unable to cope with the altered rhythms of a much slower spinning Earth. Chapter 5: Our Future, shaped by the Moon. As we project into the unimaginably distant future, the cosmic ballet between Earth and Moon continues its slow, inexorable progression. The Moon, having relentlessly braked Earth's rotation for billions of years, will continue to recede, its gravitational pull weakening with increasing distance. This ongoing recession means that Earth's rotation will slow even further, leading 2 days that are not just longer, but potentially stretching for hundreds or even thousands of hours. The familiar 24-hour cycle, so fundamental to our biology and civilization, will become a relic of a bygone era. This future Earth, with its vastly extended days and nights, will be a world transformed. The extreme temperature differentials between the sunlit and dark hemispheres could create atmospheric circulation patterns unlike anything we experience today, leading to superstorms and unprecedented climatic zones. The very oceans might redistribute themselves, responding to the altered rotational forces and the Moon's diminished, yet still present, tidal influence. Life, if it persists, will have undergone further radical adaptations, perhaps evolving new forms of dormancy or migration to cope with the prolonged periods of light and dark. Ultimately, the Moon's recession will reach a point where its orbital period matches Earth's rotational period. At this juncture, Earth will become tidally locked with the Moon, always presenting the same face to its companion, just as the Moon does to Earth today. This will be the culmination of billions of years of tidal braking, a stable, yet profoundly altered, cosmic configuration. The Moon will hang motionless in the sky from one hemisphere, while remaining forever unseen from the other. This grand narrative of Earth and Moon is a powerful reminder of the delicate balance of cosmic relationships and the awe-inspiring power of seemingly invisible forces. The subtle gravitational tug of our nearest celestial neighbor has, over billions of years, sculpted our planet, influenced the course of evolution, and continues to shape our destiny. It urges us to appreciate the unseen forces that govern our world, to look beyond the immediate and consider the vast, interconnected dance of the cosmos. What does our place in this ongoing cosmic dance truly mean for us, as temporary inhabitants of a planet constantly being reshaped by the silent, relentless pull of its lunar partner?